This is Learning Assessment Problem 321. In this problem, we are to apply nodal analysis to analyze the circuit of example 3.15. The goal of that problem is to determine the voltage V sub O. In the nodal analysis approach, we'll identify a reference node, select the bottom of the circuit, and label the other nodes V1, V2. This top node will be the V sub O voltage that we desire, and we have another node here, V3, between the voltage source and the V sub O node. So we'll begin the nodal analysis approach by applying Kirchhoff's current law expressions at the V1, V2, and V sub O nodes. We've indicated at each of those nodes the assumed positive direction for current to apply to those KCL expressions. So we'll begin at the voltage V1, KCL at V1. We'll have 2 milliamps plus V1 minus V2 divided by 4K plus V1 minus VO divided by So we'll begin with the KCL equation at the node V1, and we have 2 milliamps plus 4 milliamps plus V1 minus V2 divided by 4K is equal to 0, or V1 divided by 4K minus V2 divided by 4K is equal to minus 6 milliamps. So we'll identify that as our first node voltage equation. Now we'll do a KCL at V2. We have V2 minus V1 divided by 4K plus V2 divided by 4K to the reference node plus V2 minus VO divided by 2K is equal to 0. And this can be simplified to or our second node equation becomes minus V1 over 4K plus V2 times 1 over 1K minus VO divided by 2K equals 0. Now we can apply KCL at the VO node. We have minus 4 milliamps plus VO minus V2 divided by 2K plus VO Now we can apply KCL at the node VO. We have minus 4 milliamps plus VO minus V2 divided by 2K plus VO minus V3 divided by 6K is equal to 0. or minus V2 over 2K minus V3 over 6K plus VO times 1 over 2K plus 1 over 6K is equal to 4 milliamps. Previously we had we have the constraint equation for the node V3 voltage. V3 is equal to minus 3 volts. So this will alter the previous node voltage equation. We have minus V2 over 2K plus VO times Before writing our third node voltage equation, we should note that we have a constraint here. The voltage source connecting the node V3 to the reference node has a value of minus 3 volts. So we have that V3 is equal to minus 3 volts as a constraint. Now we'll do the KCL expression for the node V sub O. We have minus 4 milliamps plus VO minus V2 divided by 2K plus VO minus V3 divided by 6K is equal to 0. Or minus V2 over 2K minus V3 divided by 6K plus VO 1 over 2K plus 1 over 6K is equal to 4 milliamps. With the constraint that the V3 voltage is equal to minus 3 volts, we can rewrite this expression as minus V2 over 2K plus VO times 4 over 6K is equal to 4 milliamps plus V3 over 6K, which is equal to 4 milliamps minus 3 volts divided by 6K. Or our third node voltage equation is minus V2 over 2K plus VO times 4 over 6K is equal to 3.5 milliamps. Now we can write those three node voltage equations in the matrix format. We'll have 1 over 4K minus 1 over 4K, 0, minus 1 over 4K, 1 divided by 1K, minus 1 over 2K, 0, minus 1 over 2K, and 4 over 6K. That's the conductance matrix. Notice that it is symmetric about the main diagonal for this circuit. And then we have the voltage V1, V2, and VO matrix, and that's equal to the currents minus 6 milliamps, 0, 3.5 milliamps. The problem is to determine the voltage V sub O, so we can do the solution of this matrix equation by your favorite technique, and we'll obtain that V sub O is equal to minus 1.5 volts. Since you've probably solved this with MATLAB or some other technique, you also have the other answers. V1 is equal to minus 33 volts, and V2 is equal to minus 9 volts. The purpose of the problem was to compare this technique with the mesh current or loop current equation technique. In the loop current method, we only have one loop current to determine, that is the I3 loop current. The other two loop currents, I1 and I2, are known because of the current sources. So probably that approach to solving for one expression rather than writing three node voltage equations would be the simpler approach.